Section 8.4 deals with hydrohalogenation, and hydrohalogenation is simply the addition of HX to an alkene, and the HX molecule can either be HCl, HBr, or HI. It's ineffective with HF. Anyhow, if we take this alkene and we treat it with HBr at -30, you see that we add both the hydrogen atom and we add a halogen. So we add the bromine in this case, and the hydrogen is added over here. So now this alkene here is a symmetrical alkene, so we don't have to worry about regioselectivity. But if the alkene is not symmetrical, then I can get two possible regioisomers, depending on which carbon gets the proton and which carbon takes the halogen. So, the question is, with this example here I have an asymmetrical alkene. I'm adding HX. Where does the X go? Does it go to this position here, or does it go to this position here? And there's a pretty easy way to remember which carbon is going to take the hydrogen and which one will take the halogen. It says here that halogenation is regioselective for what's called Markovnikov addition. And a long time ago, a guy named Markovnikov observed that the hydrogen atoms tend to add to the carbon already bearing more hydrogen atoms. So if you take a look at the vinylic positions of this unsymmetrical alkene, you can see that this carbon has one hydrogen attached to it, and this carbon has no hydrogens attached to it. So the carbon that has the most hydrogens, and in this case, this is the only one with hydrogens, that's the one that's going to take the hydrogen from the hydrogen halide. So the hydrogen will be placed on this carbon, and then the halogen will go to the other carbon. So it says here the halogen is generally installed at the more substituted carbon. And this is a saying that my students taught me, which I like. And it says here for hydrogen, basically, the rich get richer. So the carbon that contains the most hydrogen atoms, it's the one that's going to take on the extra hydrogen atom, and the halogen will go to the other carbon atom. So when peroxides are used, though, with HBr, we get the opposite regioselectivity, and we call this anti-Markovnikov. And this is a really interesting reaction with some interesting history. So basically, it was found that when an alkene was reacted with HBr in the presence of a solvent that had been purified, they got exclusively the Markovnikov product. But when the solvent wasn't purified, they ended up with the anti-Markovnikov product. And the reason why the anti-Markovnikov product is produced in an impure solvent is because of the presence of what are called peroxides that develop over time. Anyhow, and this reaction mechanism is different, or must be different, than the one where there's no peroxides present. So anyhow, we're going to cover this reaction mechanism in chapter 10. So this is much later on. But the idea is that you have to understand what Markovnikov addition is and what anti-Markovnikov addition is. So the important lesson here, the take-home message, is that the regioselectivity of the HBr addition can be controlled. So if I take my alkene, remember it's an unsymmetrical alkene in that this carbon already has hydrogens attached to it. So if I do my hydrohalogenation, so I add my HBr, I get Markovnikov addition. So I added the hydrogen atom on this carbon. And if I do anti-Markovnikov addition, all I have to do is take my HBr, and then I also add peroxide to the reaction mixture, and I get the anti-Markovnikov reaction. So these are two sets of reagents that you should be familiar with. So you should know that if you want to do Markovnikov addition, you would just add HBr like this, and if you want to do an anti-Markovnikov addition, you would use HBr and peroxides. Very important reactions in organic chemistry. So let's take a look at some problems here. It says, draw the expected major product for the following reaction. So you can see that all three of the alkenes that are on this slide, they're all being treated with a hydrogen halide, and they're all unsymmetrical alkenes. So if I take a look at the first one, if I look at the two carbon atoms in the double bond, I can see that the first carbon, or the one on the top here, has no hydrogens attached to it, whereas this one has one hydrogen attached to it. So we're going to go by the rich get richer rule, and my bromine is going to be attached to this carbon, and of course my hydrogen is attached here. Now normally I wouldn't draw those in, but those are just for instructional purposes only. So again, the same thing applies with this one. So if I take a look at this carbon, there are no hydrogens directly attached to it, right? There's a methyl, there's a methylene here. But if I look at this carbon, yes, there's a methyl group, but there's also a proton. So again, we're going to follow the rich get richer rule. So my bromine atom will be attached here. And then finally, for the last one, the same thing applies. So this one is the carbon. It's the only carbon that has a hydrogen attached. So again, the rich get richer. So this carbon is the one that will take the extra hydrogen, and I end up with my 1-chloro, 1-methyl cyclohexane. There we go. So these are all Markovnikov addition, and sometimes I just abbreviate this as Mark. So Mark addition. There we go. So let's talk about the mechanism for a second here. So the mechanism is a two-step process. So in the first step, we have a proton transfer. It says the alkene is protonated, forming a carbocation intermediate and a bromide ion. And you're saying, well, if the rich get richer, this is the carbon that has a proton. So I'm going to add the proton here, the teal-colored proton, to this carbon atom. So I end up with this tertiary carbocation, and then the bromide can come in and function as a nucleophile to make the alkyl halide. So the step with the highest activation energy, this is the rate determining step. And the rate determining step is the formation of the carbocation intermediate. So the proton transfer, this is the rate determining step. And then the nucleophilic attack, the potential energy of its transition state is lower than that of the proton transfer to produce the carbocation. So recall that there are two possible products, the Markovnikov and the anti-Markovnikov product. So if I were to draw the mechanism of the pi bond attacking HX and taking on the proton, or the alkene becoming protonated, I end up with a secondary carbocation. So this is a secondary carbocation, whereas if I draw the mechanism using the Markovnikov pathway, then I get a tertiary carbocation. So this is tertiary. So the Markovnikov product is formed solely based off of carbocation stability, and a tertiary carbocation is more stable than a secondary carbocation, and this explains why we form the Markovnikov product when we treat an asymmetrical alkene with HX. Let's take a look at the stereochemistry associated with hydrohalogenation. So it says here that hydrohalogenation may result in the formation of a chirality center. So if I take a look at this molecule, I have these 3 protons, so the rich get richer, and this is the carbon that takes the hydrogen from my HCl, and my chlorine ends up on this carbon here. So now I have a chiral center. So it says here there are actually 2 Markovnikov products that are formed in this reaction, so I get a mixture of enantiomers, the R and the S, and they're formed in equal amounts. So let's take a look at why that must be. And if we look at what happens is that the carbocation intermediate that's formed is sp2 hybridized. So if this carbon is sp2 hybridized, it has an unhybridized p orbital, and the molecular geometry of the carbocation is trigonal planar. So if it's planar, which is represented by this sort of plane here, that means that the nucleophile, okay, it can attack from either face of the molecule. And this is why I end up with both enantiomers. So I get the product from attack on the top face of this molecule, and I get the product from attack on the bottom face of the molecule. So that's why we end up with a mixture of enantiomers. So also a little bit about rearrangements. So you remember carbocation rearrangements, and the 2 that we look at are the hydride shift and the methyl, or sometimes called the methide shift. And the reason that carbocations rearrange is when they can become more stable. So if I take a look at the mechanism, if I take this alkene and I look at the first step, so my pi bond takes on the proton, so I do my proton transfer, I lose the chloride as the leaving group, I end up with a secondary carbocation. But what's going to happen is I'm going to get a hydride shift in this case to produce the more stable tertiary carbocation. Then I get my nucleophilic attack by the chloride to give us the final product. So it gives us this product. And it says here that when this alkene undergoes hydrohalogenation, the secondary carbocation could rearrange to give you a more stable tertiary carbocation. But what you'll find is that most of the time you end up with mixtures of products. says when carbocation rearrangements can occur, they do occur. So here's a perfect example, the reaction that we just looked at. And in fact, you get about 60% of the rearrangement product and about 40% of the non-rearranged product. So again, this might seem like it's synthetically not useful, but if you have a substrate which will not undergo carbocation rearrangement, hydrohalogenation is still a very useful reaction. Let's take a look at question 8.2. It says, identify the reagents that you would use to achieve each of the following transformations. So you can see that in both cases, I'm starting with the same alkene, and I'm doing a hydrohalogenation. I'm adding HBr to both of these molecules. But you could see in the first example that this is a Markovnikov addition. And if you're wondering why is this a Markovnikov addition, you remember the rule that the rich get richer, and this carbon has 2 hydrogens attached to it, and this carbon has no hydrogens directly attached to it. So the way that we do Markovnikov addition for the addition of HBr is just to treat the alkene with HBr. That's it. That's all. In the next example, you can see that this is the anti-Markovnikov addition product. And how do we get that? Well, we treat it with HBr, but in this case, we have to add peroxides. And that's a mechanism that we'll study in detail in Chapter 10. The take-home message from this question is that you should know the reagent for Markovnikov addition of HBr, and you should know that when you want to affect an anti-Markovnikov addition of HBr, that you use HBr and peroxides. So we just call this peroxides.